Welcome back. We're going to let vector u be negative 1, 42, and 14. Matrix A be 3, negative 5, 2 for the first column, negative 1, 9, and 2 for the second. Is u in the plane in R3 spanned by the columns of A? So we have R3. So what we're going to do is we're going to set up matrix A times X and set that equal to U in an augmented matrix form. All right. Excuse me. Okay, so let's take matrix A. It has columns 3, negative 5, 2, negative 1, 9, 2, and then vector U. If we row reduce, and you can do that on your TI-84, you're going to get pivots, and you'll see that it's consistent. X2 is equal to 5.5, X1 is equal to 1.5. Since X is consistent, then yes, U is in the plane in R3 spanned by the columns of A. There's a pivot in every column. Note, if you come up with an inconsistent matrix, then U is not spanned. Also, make sure you note there is a pivot in every row. This one's a 0 row, so you don't have to sweat that one. Let's look at a second example. Let's let matrix A be a 2 by 2 and matrix B be a 2 by 1. How can it be shown that AX equals B doesn't have a solution for some B? Let's row reduce matrix A to show it doesn't have a pivot in every row. Remember from the previous video, we look for pivots in every row. That means the columns of A span RM. In this case, R2. So we're going to set up matrix A. Its first column is negative 3, 12. Matrix A's second column is 1, negative 4. And then we're going to throw B in to make it augmented. If you row reduce this, 4 times row 1 plus row 2, 4 times negative 3 plus 12 is 0. 4 times 1 plus negative 4 is also 0. Well, if this is going to be consistent, this also has to be 0. So 4b1 plus b2 has to be equal to 0 in order for AX equals B to have a solution. If this is not, then from a few videos back, if you have a row of all zeros except for the last entry, then it's inconsistent. A system of equations is said to be homogeneous if it can be written in the form AX equals 0, where, look, glance down at the middle, like this is an example, you'd have every equation set equal to 0. A is an m by n matrix, and 0 is the 0 vector with however many entries you need to make the multiplication possible. There's always at least one solution, and that's if you were to just make all the x's 0, then the answer has to be 0. In a real number system, if you take a number times 0, you'll get 0. So this is the matrix kind of equivalent. If that 0 matrix is one of your solutions, which it will always be a solution, that one's called a trivial solution. The important question is whether there exists a non-trivial solution, which is a non-zero vector that still satisfies this equation. The homogeneous equation AX equals 0 has a non-trivial solution, meaning something other than all zeros, if and only if the equation has at least one free variable. That means one of your variables doesn't have a designated numerical value. We looked at that a few videos ago. Let's look at an example. Determine if the homogeneous system has a non-trivial solution. We have three equations with three unknowns. Let's take all these coefficients and write them as an augmented matrix in the same positions. If you go into your calculator and you type in this 3x4 matrix and row reduced echelon form using your TI-84, notice because they're all zero, we're going to have infinitely many solutions. But let's look at these pivots. x2 is equal to 0. If we bring this over, x1 is equal to positive 4/3 x3. Well, x3 is free because the third column, there's no pivot. Well, let's go back up here. Back here. The homogeneous equation has a non-trivial solution if and only if the equation has at least one free variable. Well, we've got a free variable. If you translate this out where x1 is equal to 4/3 x3, x2 is 0, and x3 is the free variable, the solution vector x, which will have three entries, the first entry is 4/3 x cubed, the second entry is fixed at 0, and the third one was free. If you were to say factor out that x to the x3, then you're going to be left with 4/3, 0, and 1, which is a line through 0, or the origin, in R3. This is your non-trivial solution. Any scalar multiple of it, which means any number for x3, would fall on that same line. It would have a different length, possibly a different direction, but that's how you tell whether you have a non-trivial solution, is you set it up, row reduce it, and if you spot a free variable, then the 0 vector is not your only solution. That one. Describe all solutions of the equation 10x1 minus 3x2 minus 2x3 equals 0. Okay, so if we isolate x1, and that's just one in particular, x1 is equal to 0.3 x2 plus 0.2 x3, and we do that by moving these two terms over. They go from negative to positive, and then dividing everything by 10. Okay, so x1 is equal to the addition of these two vectors, which have weights 0.2 and 0.3. There's x1. x2 and x3 are free. Notice we've got them in terms of x2 and x3. x2 is multiplied with 0.3, an unwritten 1, and then there's no x2 in that third position. x3 in the first position is multiplied by 0.2. This entry does not have x3, so that's 0, and then this one's an unwritten 1. These are the two vectors that can be scaled, creating a span, and that's your solution set. If you were to graph these two vectors and span them out, for example, vector u, vector v, now they're different, so they're not going to be on the pointing in the same direction. So U, V, remember our parallelogram rule, so it's like a sheet of paper. That sheet of paper represents the span of UV. If it's an infinite sheet of paper, of course, but it's a plane that goes through the origin. Note, if your homogeneous equation AX equals 0 has only one free variable, the solution set is a line through the origin, as in the example of before the one above. That was one where we had an x3 times one vector, so that's what that ending paragraph here means. All right, so let's recall that our system of equations we just solved had the solution set x equals x3 times v. This was the one I was talking about being a line through the origin instead of a plane through the origin. It only had one vector spanning the solution set. So it's a line through the origin instead of a plane through the origin. Okay, so our solution vector to the homogeneous equation, it wasn't the trivial one, it was x3 times v, specifically v being this vector. This can be written in parametric form where x is equal to t, which is some constant, times vector v. T is going to be a real number. Also, the implicit equation that we did in the previous example, where we had two vectors, u and v, and our solution set was the span of those two. x2 and x3 could be, they're free variables, so they can be any constant value. But the span of those two vectors, if you were to write these in parametric form, your weights, x2 and x3, would be called, say, S and T. Vectors u and v, the span of those is your solution set, but any scalar multiple, where S and T are real numbers, that's just the parametric form, parametric vector form, that means the same thing.